Right, today I want to have a look at how we go about applying some of this local maximum, local minimum differentiation stuff. So I've got a nice example here. So here we go. I'll draw a picture. This is a wall, and Bob the farmer wants to create a fence. So what color? Purple's nice. And he wants to create a rectangular paddock for his ducks. So his ducks are going to go in here. And he can build it against that wall, so he doesn't need fencing along the wall. What he's got 30 meters of fencing material. And he wants the maximum possible area for his ducks. Right, so the first thing we need to do is to set up an equation for this. So we'll do that. So I'm going to label this y, and that's a y, and that's an x. So you can see there that x plus 2 lots of y is equal to 30. We know that because that really is the amount of fencing that we've got. 2 y sections, 1 x section gives us a total of 30. The area, of course, the area is just going to be x times y. So, and that's what I'm working on. Area is equal to xy. That will be the thing that we need to differentiate. But I can't differentiate it as it is because it's got 2 variables. It's got x and y in it. So we're going to rearrange this top equation to make x the subject. So this one, I'll do that down here, a little messy. So x is going to be equal to 30 minus 2y. Okay, so 30 minus 2y, just by subtracting 2y from both sides of the equation. And then we will substitute that wherever I see an x in that equation here. So we're going to make a substitution. So if I do that, the area then is equal to 30 minus 2y and times y. And we should multiply this out before we try and do any kind of differentiation to it. So I get 30y minus 2y squared. Now this is a little bit different already in that the variable that we've suddenly got is y. But it doesn't matter, as long as I've got a single variable, we can differentiate this. So, you know, you could have labeled the W and L or W and H for width and height or something or other. So you don't have to use X and Y. Differentiation and calculus works with any variables. X and Y are just sort of ones that we use all the time. They're kind of convenient old friends, but you can use P and Q, R and S, and we do, depending on the situation. But this time we'll continue with X and Y. And we're going to go ahead and differentiate. The other thing, of course, I've got A here. And so, but I can differentiate A, and we're going to differentiate A with respect to Y. So this becomes 30 when I differentiate that, and that becomes minus 4y. And here's the process. So we better write down the process to going ahead and finding the maximum area. One is that we're going to differentiate. 2, we're going to set it equal to 0 because we're trying to maximize an area. So what I want is I want to work out where is the local maximum. Where is the local maximum? So we'll continue with that, and we'll set this equal to 0. Wrong color. Go over the top. 30 minus 4y is equal to 0. And that'll work out whether we've got a local maximum or a local minimum. So it's 30 minus 4y is equal to 0. Therefore, 4y is equal to 30. And when we divide that by 4, I get y is equal to 7.5. All right, so we've done that. So we've now got y is equal to 7.5. We can work out what x is by substituting into this equation over here. And if we do that, then I get x plus 2 times 7.5 is equal to 30. And when we solve that, we find x is equal to 15. So what I've got now is I've got turning point at x equals 15 and 7.5. So that is the coordinates of that turning point where I've got a local maximum or a local minimum. Now, but what is it? Because I want a maximum. So we can't always assume that that's a maximum. So how do I know it's a maximum? Well, if we go back and have a look at this function here, and this is the function that we created, I can put an A in there even, then that is an upside down parabola. I know it's an upside down parabola because the highest power is the square here. So I've got this power of 2 right there, and it's negative. And so if it's negative, we've got an upside down parabola, and an upside down parabola always produces a local maximum. So when you're answering this question in an exam setting, a little drawing like that is all you need to prove that you have shown that it is a maximum. And sometimes you're not asked to prove it. So there it is. So the local maximum that occurs, so when x is equal to 15, y is equal to 17.5. Well, what is that area? Because we're asked to find the maximum area. So it just becomes 15 times 7.5. On the calculator, it tells me it's 112.5, and that would be meters squared, because I think we had meters there, which we do. Look at that. That's how we apply these things. I better just finish off actually. What else do? We set it equal to 0. We solve, okay, in other words, solve for a variable. And then 4 really is we calculate whatever that is, okay? So dot, 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 to show you that you need to calculate the area or calculate the height or calculate the cost or whatever it is that finish off the problem.